I'm a physicist, a computational physicist at Caltech, and I work in a variety of programming languages. In my undergraduate degree at MIT, I studied both computer science and physics, and it's great to work at the intersection of the two. I also had another life as a mobile developer for applications like Circle of Six and Signal. So I'm definitely getting a lot out of this Polyglot conference. Mostly the languages I'm going to be giving examples in today are C, C++, even Fortran, a little bit of CUDA. And that's the high performance in the title. And to start out with, since some people might not have done much parallel computing in the past, I'll give a little introduction to what exactly that might mean. So you could have shared memory or distributed memory. You could have single instruction, multiple data, or multiple instruction, multiple data. You could also have functional parallelism, where different tasks are broken up and executed in parallel that may not have dependencies upon each other and then combined in the end. In high-performance computing, we mostly deal with distributed memory and multiple instruction, multiple data. That would be, you might have multiple networked machines, which each individually have their own memory and data store, perhaps even a shared hard drive, a networked hard drive as well, and you want to perform some computation on that machine. Mostly the languages of choice are C, C++, and Fortran, again because of performance, but I'm really excited about languages like Julia, which we're going to hear about. I believe your talk's been moved tomorrow, and other languages that will give us, as programmers, I think we're all going to be forced into this era of distributed computing, whether or not that's high performance, as Moore's law kind of comes to an end, and we're going to have to be leveraging multiple cores on the same machine, of course, but also eventually probably distributed memory systems to get the performance that we need. So one standard that is often used with these languages, of course, the standard can also be implemented in other languages, is the message passing interface, or as well MP. And for distributed memory and single instruction multiple data, potentially CUDA, which is a GPU programming, higher level programming language to allow you to execute the same instruction on a lot of different data at once, originally used in the gaming community, of course, but now we've leveraged that for scientific computing as well. So in parallel computing, you might want to quantify how much faster an algorithm will run on a parallel computer with n processes, and TP is the time it takes to execute the algorithm on P processes. So here you would have the speed up, the ratio between the time it takes on one process to the time it takes on n processes. And generically, every algorithm, let me go back here, every algorithm has some serial component, and minimizing that serial component is what will give you the best speed up. So as processes are added to the computation, a decreasing return may be seen on algorithmic speed because that serial component will begin to come into play. So if S is the fraction of the algorithm that's inherently serial, then the algorithm will instead have the following speed up upper bounded by 1 over S. If you take the limit as n, your number of processes goes to infinity. So fundamentally, you're upper bounded by this serial component. This is just a visualization of, I'm not going to talk about this parallel visualization framework called ParaView today, but it's an open source visualization framework that allows you to visualize terabytes or even more of data on a distributed computer. But I like this visualization of this algorithm. Basically, we have 4 processes, and these are actually different computers. And we can see that prior to this algorithm being run, when the data was initially read in, that in the center, there was a lot of mixing between where the data was located on different processes. And for many algorithms, this creates a problem. For example, if your algorithm depends on neighboring particles or neighboring elements, then you might have to query another machine to do that. So one way to speed up your algorithm might be to first try to minimize the number of processes, the kind of mixing of the processes. And another nice concept from parallel computing is the concept of ghost faces. So here's a little Space Invader divided on 3 processes. And then I want to run an algorithm that finds the boundary of the Space Invader. And if I were to do this in parallel and then recombine it, I would get a lot of spurious boundaries. However, if I go ahead and on the Space Invader on the right-hand side, I add in some white blocks, where a white block is always added if it used to be next to another block on another process called a ghost block or a ghost node. And then I do the same algorithm. Then I throw away the ghost blocks, and then I recombine it, I get the right result. So that shows that by adding, paying some cost in terms of memory, in terms of storage, you can create some algorithms that nevertheless function as planned if you throw away these ghost zones when you're done. It's a little bit of a complicated formula, but this is an example, a simple example from physics, where if we want to find the center of mass, let me parse this out for you. Basically, I'm going to sum up the mass of every particle, and then I'm on the bottom, then on the top of that formula, I'm going to multiply the mass of the particle times its coordinate, where I is referring to x, y, or z coordinate. So then you would get the center of mass in the x, y, or z direction. And the important thing about this algorithm is that it really doesn't depend on any neighboring particle per se. You could have each, you could break up your data into n chunks, have each chunk compute this quantity on its individual portion, the top quantity and then the bottom quantity, and then communicate the result and compute the final sums of the top and bottom quantity to get the final result. So it very neatly parallelizes because it's a commutative operation. And the processes can calculate those top and bottom sums independently, and the result is combined and final division is performed. You can either do that naively by sending everything to some root node, or you can combine it in some binary structure, which languages or standards such as the MPI actually support those operations. You can think of it, if you're familiar with MapReduce, as a reduce operation of sorts, done very efficiently. So this is a nice algorithm, and more hairy algorithms are ones that really depend on many communication steps, because not only are you killed by serial components, you're also killed by communication, especially as you scale up. Okay, so a little bit of an example of MPI, if you haven't seen it before. It has some of this, I believe most people in the audience would be more familiar with MapReduce than with MPI, but you have the ability in the language, in something that implements the standard, to tell which node you are, which process you are, 0 to n. And you have the ability to broadcast messages. So you have the ability to broadcast the result of your computation to everyone. You have the ability to collect results. You have the ability to send your result to a specific process. And you have the ability to recognize if you're the root process as well. We need some comedic relief in a talk that's going to feature so much Fortran. Fortran can't be the only joke in the talk. Okay, so you also have the ability to erect barriers. So that's basically like a synchronization step. So you can do a blocking send, or you can do a non-blocking send or receive, where you send data or receive data, but you don't wait. And then, of course, you have to check whether you received the data or the data has properly been sent before you actually go to do something important with it. But you're able to do other computations in the meantime. Okay, so here's some C code, and we see a couple, you can just look at the comments. So basically we can start out with an initialization, we can find out how many processors we have, we can find out what the number of process that this is, and the same, with an MPI exec command, the same code runs on every different node. It's just that the result in terms of my ID will be different. Numprocs will be the same for everyone. So then we can actually do something with that. We can print something, and you'll get this printed, and you can receive data and send data. And here, everyone receives something from the root processor, in this case rank 0, and then sends some information to rank 0. So that's a little bit of MPI. We also have OpenMP. So this would be doing the same kind of thing, but locally using threads instead of a distributed machine. And here we can see the number of threads that we have and say hello to everyone else. So here's a little bit of CUDA. So CUDA is, again, distributed computing on a GPU. So here you have the concept of host memory, which is the CPU, and device memory, which is going to be your GPU. And there's a special instruction to allocate memory on the GPU. So once the memory is allocated, then you can go ahead and copy information there. And then there's this concept of a kernel on a GPU, and I'll show you some kernel code later. But basically, we're going to add on all n portions and copy the result back to the host, which is our CPU, and then free the memory. Here we didn't actually do anything with the computation, but we could eventually. So here's a little bit of a small kernel, and you can see that it's quite simple, and the only thing different from your standard C is this global keyword. So CUDA is basically an extension of C that you compile with a CUDA compiler, but it's basically straight C with some small little extras. So that's a little introduction to some of the tools of the trade in high-performance computing. So what do we actually want to do with these? I'll give an example from my field, which is solving differential equations on a grid. So sounds kind of complicated, right? And here's some more complications. You might remember from calculus, if you ever did take calculus. If not, I'll teach you calculus in 1 minute. So we have 2 points on this curve, and we want to find the slope between those 2 points. Actually, calculus would tell us the slope of the line that doesn't touch the curve at any point. So say that red point. So calculus would tell us that result, but we don't want to do calculus, so we're going to do our best guess, and we're just going to take 2 points kind of near the red point and draw a line between those and say that that's basically the slope. And then the smaller we make that line between the 2 blue points, the closer we get to the result that calculus would give us. And now calculus is continuous, and computers are discrete. And so mostly we have to do the discrete thing on our modern computers. And so we can do this in a more complicated manner in 3 dimensions, using volumes if you want to compute volumetric things, but this is the basic idea. If you want to solve a differential equation that is some equation involving these funky derivatives, you might create a grid and then do some approximation like this to try to get those derivatives, and then go ahead and solve your equations with regular algebra. Okay, so here's an example solving something called advection, basically moving material from one place to another. And if our computers were perfect, if you had this much material, 1 Christine here, and then I put it into an equation and figured out where I was here, you would get 1 Christine here. In practice, we have errors in computation, so you might get like 99.999% of Christine here and a little bit that went to numerical error. But this is a way that you can test. If you move material over time from A to B, you should get 100% of the stuff at B if you moved 100% of the stuff. We can actually do that with an equation and test how good our algorithms work, or sometimes you actually want to do that to solve various physics things such as heat transfer. Okay. So that was a little bit on a 1D grid, and then I said you could do it for 2 dimensions or 3 dimensions and with volumetric stuff. In practice, if you have, say, billions of particles like we do on the left here, you might not want to have a regular grid everywhere because that would be a very large grid. So we sometimes do something called adaptive mesh refinement in these grid-based methods where you follow where the most particles are in terms of where you create your grid to do numerics. And that's called adaptive mesh refinement. And then you can kind of have big grid cells where you don't have a lot of stuff and small grid cells where you do have a lot of stuff. Okay, so those are some examples of differential equations, but these come up in chemistry, biology, biochemistry, physics, fluid dynamics, environmental simulations, weather forecasting, geophysics, space science, astronomy, artificial intelligence, all sorts of really cool stuff. And being able to solve these on supercomputers gives us insight scientifically to any of these fields. Traditionally, physics has kind of led the way because we had a lot of computer-inclined people already in the field. Also, weather forecasting kind of depended on it very early on. But nowadays, biologists and chemistry folks are getting into the fray as well. And it'll be very exciting as we see some of these. We've already seen with coffee and other things that GPU accelerated or other high-performance computing techniques in artificial intelligence will hopefully result in some very cool stuff in the next few years. Okay, so in the last part of my talk, I'll do what I promised to do and introduce a framework that allows physicists or other scientists who want to solve these differential equations on large grids to do so very efficiently in the high-performance computing language of their choice. And that is the Cactus framework, which is a modular open-source environment for scientists and engineers that allows parallel computation across architectures, common code development across groups and languages. Okay, here's a cactus, and it's named this because there's flesh, which is the root part, and that has a bunch of APIs, allows you to define parameters, has a scheduler, grid variables, it has a whole make system and error handling. And then there are things called thorns, which are more modules, which allow people to define their own parallelism, coordinate infrastructure, I/O, etc. Interpolation, various types of equations. And so most of the use of this toolkit, there's a set of core developers who work on the flesh, but mostly people work on these modules. And the make system allows you to very easily select which modules you want to use and as well integrate other people's modules. And I'll show you that towards the end. Okay, so what is the thorn? It contains cactus declarations in a special language, the source code, which can be any of these languages. I believe it is said to be very easy to add an additional language. No one has found the need yet to do so, but it is certainly possible. Make file fragments, documentation, and test cases, as well as example parameter files. So once an executable is built, there are some options you can change at runtime in parameter files. Okay, so the API of the thorn is defined in this Cactus programming language, essentially called interface.ccl. And it has the name, the implementation name, various grid functions. It can inherit grid functions and routines, which are basically the APIs that are provided or used. There's also the scheduler, which calls routines at certain times. So the main thorn, the execution body of the flesh, will go through things in a various sequence, and you can kind of insert your own computations in that sequence. And schedule groups can be created, so you can have a whole group where you say execute this entire group at the same time, and you can also synchronize variables. So it's rule-based, where you can schedule after, before, or while, and it also allocates storage for the grid variables. Okay. So your parameters are basically the runtime options that I mentioned that you can set in the parameter file. You can also provide defaults when you define your thorn. So you can declare parameters. There are 5 types: integer, real, Boolean, keyword, and string. You can define allowed ranges where it will basically give a warning or crash without proper data. Basically, it will stop running and say, hey, we only accept this parameter within this range. For example, in this example, the amplitude must be non-negative. So if the user tried to give a parameter file with -1 there, it would stop running and say, hey, in your parameter file, this has to be non-negative. And it can also inherit public parameters from other implementations. So this is an actual example of a parameter file. So each of the things on the left are various thorns, driver or grid, AD and base, these are all thorns. And then : the actual parameter that you want to set, and then equals whatever you're setting it to. And at the top, you have the active thorns. So that is basically because even if you compile a range of thorns, you don't necessarily have to activate them all at the same time. This will set your parameter values. So here's a little bit of example source. I'm not going to show the whole thing. I'm not going to show anything. Party time. Okay. All right. So here. All right. I'm going to troubleshoot for 1 second. All right. Disco. Okay. So here's just a little bit. It's a subroutine that's within a particular thorn. It inherits a bunch of arguments from everywhere else, and then it declares some local variables, does some computations, and this can be used within that thorn or called from other thorns, which depend upon it. Okay. So the driver is part of the flesh, and it's a specialized thorn for memory management and parallelization that contains all this information about the grid. So I showed you how you might want to solve differential equations on a grid before. You might not want to design all the parallel infrastructure to do that, and that's why Cactus is great. So in that case, you can use a multi-block refined grid structure and just basically say, oh, I want this portion of the grid to the left or the right of me, or above or below me, et cetera, and not have to worry about doing all the efficient parallelization there. And things that are driver specific are interpolation, reduction, I/O, and checkpointing. Okay, so we're to the last few slides, so no worries about me boring you with high performance computing. So I promised some polyglottery, how the Cactus is made. So these CCL files are parsed by Perl scripts. Now Cactus was designed in the 1990s originally, and it still is mature almost decades later, which is impressive. And it then creates from these CCL files the interface, the params, et cetera, C code and LaTeX files for documentation. The make files require GNU make, and the flesh is written in C. The thorns you can write in C, C++, or Fortran. Each different module can be, each of the thorns can be in any one of these languages, and even a combination of those languages. And more can be added. So the flesh helps with the function calls between the different languages and really enables the developer to write and build upon the modules of their choice in their particular thorn while still leveraging all the infrastructure and modules written by many other people in the community. And the Fortran code is pre-processed with C++, combining Fortran with C++. You thought it couldn't get worse. And then we sanitize it with Perl. I don't think that's sanity. Okay, anyway, documentation uses LaTeX. So you'll get, after you compile it, an entire documentation in PDF and beautiful LaTeX with mathematical formula if you put those in your docs. Okay, so that was how the Cactus is made, so how to make the Cactus. So on the right, this is just highlighting that we have one thorn that's using particularly one SVN server in Germany, and I even have a username where I have a specialized, I have basically access to that server via my public SSH keys. And then I'm checking out a particular thorn. And then right below, there's another thorn where it's a it's a Git repo on a Bitbucket account where there's no username. So you can do a variety of these things. And when I'm actually building code to run a simulation, I'll have hundreds of these perhaps. So it's very nice in that you can integrate even multiple types of version control on multiple servers with multiple different types of authentication or no authentication. And then you give it this thorn list. You can even build different configurations in the same tree. So I might want to have one configuration for one simulation and another for another. I don't have to check out multiple copies. And you can choose a list of thorns and options for each configuration. And of course, as I mentioned, different version control systems and repository locations. Okay, so what is this all used for? A variety of things. I mentioned a lot of different applications. It was primarily the numerical relativity community who basically had to go this route to solve their very gnarly differential equations. Came up by Einstein, so don't give him access to your differential equations. He'll make them too complicated. Okay, so black holes, neutron stars, supermassive stars, gravitational waves, quantum gravity, supernovae, all sorts of things. This is a star exploding with magnetic fields on the right, and that was all done in a simulation using the Cactus framework and one particular group of thorns called the Einstein toolkit. But people are using this in a variety of different fields as well. So you can do very powerful things with this framework, and I think something that we can take away as well is the fact that as a scientist or as a programmer, you're allowed to work in your preferred language and yet integrate with APIs from a variety of different languages, which is neat because you can build on legacy code without having to write everything in Fortran. So I write almost zero Fortran, but I get to deal with Fortran and not have to rewrite and parse and port everything to C or C++. And even if you are writing Fortran, you don't have to write everything in Fortran 77 or Fortran in the time of Jesus. Okay, so here's a little picture of some cacti, and I will take a few questions if you have any. If not, I'll be around all week. I'm based in Los Angeles. I'm Corbett on Twitter, and I work with Kip Thorne, the producer of Interstellar, and at the university that Feynman used to work. So it's a pretty cool place to be. All right, thanks.
Just to clarify, so when you have multiple languages interoperating, that's via old school Unix linking?
So the multiple languages interacting, I believe the Fortran is actually parsed into C++ at some level. Something nuts like that, yeah.
Okay, so everything gets built into C++ and then built from there?
Yeah.
Hi. So I was wondering, how much time usually does the design of the equation take compared to development of it in the pure code?
So
or do you design like in code already?
Yeah, so the equations are mostly well known, and the question is how many of them can you solve at once efficiently? And what approximations you need to make. So one example just from gravitational physics is to solve the gravity equation directly. It's an order n squared problem where every particle depends on every other particle. And that works for objects up to the scale of, say, globular clusters, balls of stars. They have millions of stars. But if you want to try to simulate portions of the universe, you end up having to sample with billions of particles. So you have to make approximations and say, well, actually, it's an n squared problem, but we're going to make approximations where we group particles out here all in one single particle. It's called a multipole method. So the majority of the time is not spent on maybe developing equations, but more trying to find the right approximations for the right problem and trying to quantify your errors, because you don't want to make the effort of computing something exactly if your numerical error is above that, for example. So just figuring out what you really do have to solve to get the physical result is, I would say, the majority of the time, and then how to do that and implement that is another portion.
Hi, thanks for the talk. This is just a side question, but what is the coolest scientific discovery that was made with the Cactus framework that you know about?
I think there's been a lot of cool research into how black holes collide, for example, and predictions. One thing that I'm working on is how to predict how the first supermassive black holes might form. And I think that's going to be pretty cool. So I would say the coolest discoveries are yet to be made, but there have been a lot of fundamental theoretical predictions. The thing is that the majority of these will not be verified until the gravitational wave observatories get a little bit more sensitive, and that the primary prediction in this super strong general relativity regime is a radiation of gravitational waves, and we're still not able to observe that with enough sensitivity. But there are detectors in the US, LIGO, eventual space detectors, ELISA, that should observe this. So there are a lot of predictions that the community is making that once you see the spectrum, you'll be able to say, oh, those are two black holes merging. You'll be able to say exactly what it is because of predictions that we've made. Otherwise, you would just look at this thing and say, oh, I don't know what these waves mean. So, yeah.
Anyone? Questions?
Someone down here.
Oh.
Would you code something scientific in JavaScript?
I mean, JavaScript does have fairly good performance as compared to, say, Java. And I have seen people code scientific things in Java, but more for demonstration or educational purposes. I definitely think that there are neat demos where you can do unexpected things in JavaScript, and that would be a various demo, but at some point when you want to scale things up, you're going to want to run on a distributed machine. You won't be able to scale that with JavaScript. But what I would do scientifically with JavaScript is, so for example, I mentioned this parallel visualization framework. The front end for that is built on Qt. And you know, Qt is a little bit of a pain to build. If you've ever tried to build it, it does often build 90% of the time, but it takes like 4 hours to build. So if you want to do like rapid iterative development, front-end tools where you have a client-server architecture and the JavaScript is the client hooking into a server that the backend is some HPC cluster, JavaScript would be very well suited for that, in my opinion.